Our world is made up of patterns and sequences. They're all around us. Day becomes night. Animals travel across the earth in ever-changing formations. Landscapes are constantly altering. One of the reasons mathematics began was because we needed to find a way of making sense of these natural patterns. The most basic concepts of maths, space and quantity, are hardwired into our brains. Even animals have a sense of distance and number, assessing when their pack is outnumbered and whether to fight or fly, calculating whether their prey is within striking distance. Understanding maths is the difference between life and death.
But it was man who took these basic concepts and started to build upon these foundations. At some point, humans started to spot patterns, to make connections, to count, and to order the world around them. And with this, a whole new mathematical universe began to emerge.
This is the River Nile. It's been the lifeline of Egypt for millennia. I've come here because it's where some of the first signs of mathematics as we know it today emerged. People abandoned nomadic life and began settling here as early as 6000 BC. The conditions were perfect for farming.
The most important event for Egyptian agriculture each year was the flooding of the Nile. So this was used as a marker to start each new year. Egyptians did record what was going on over periods of time. So in order to establish a calendar like this, you need to count how many days, for example, happened in between lunar phases, or how many days happened in between two floodings of the Nile.
Recording the patterns of the seasons was essential not only to their management of the land, but also their religion. The ancient Egyptians who settled on the Nile banks believed it was the river god Hapi who flooded the river each year. And in return for the life-giving water, the citizens offered a portion of the yield as a thanksgiving.
As settlements grew larger, it became necessary to find ways to administer them. Areas of land needed to be calculated, crop yields predicted, taxes charged and collated. In short, people needed to count and measure.
The Egyptians used their bodies to measure the world, and it's how their units of measurement evolved. A palm was the width of a hand, a cubit an arm length from elbow to fingertips. Land cubits, strips of land measuring a cubit by 100, were used by the pharaoh's surveyors to calculate areas.
There's a very strong link between bureaucracy and the development of mathematics in ancient Egypt. And we can see this link right from the beginning, from the invention of the number system, throughout Egyptian history, really. For the Old Kingdom, the only evidence we have are metrological systems, that is, measurements for areas, for length. This points to a bureaucratic need to develop such things.
It was vital to know the area of a farmer's land, so he could be taxed accordingly. Or if the Nile robbed him of part of his land, so he could request a rebate. It meant that the pharaoh's surveyors were often calculating the area of irregular parcels of land. And it was the need to solve such practical problems that made them the earliest mathematical innovators. The Egyptians needed some way to record the results of their calculations. Amongst all the hieroglyphs that cover the tourist souvenirs scattered around the city of Cairo, I was on the hunt for those that recorded some of the first numbers in history. They were difficult to track down. But I did find them in the end. The Egyptians were using a decimal system, motivated by the 10 fingers on our hands. The sign for 1 was a stroke, 10 a heel bone, 100 a coil of rope, and 1,000 a lotus plant.
Yeah, how much is this T-shirt?
25.
25.
Yes.
So that would be 2 knee bends and 5 strokes.
Yes.
So you're not going to charge me anything up here?
Here, 1 million.
1 million?
Oh my God.
No.
Is this 1 million?
1 million. Yeah, that's pretty big.
The hieroglyphs are beautiful, but the Egyptian number system was fundamentally flawed. They had no concept of a place value, so one stroke could only represent 1 unit, not 100 or 1,000. Although you can write 1 million with just 1 character, rather than the 7 that we use, if you want to write 1 million minus 1, then the poor old Egyptian scribe has got to write 9 strokes, 9 heel bones, 9 coils of rope, and so on, a total of 54 characters. Despite the drawback of this number system, the Egyptians were brilliant problem solvers.
We know this because of the few records that have survived. The Egyptian scribes used sheets of papyrus to record their mathematical discoveries. This delicate material made from reeds decayed over time, and many secrets perished with it. But there's one revealing document that has survived.
The Rhind mathematical papyrus is the most important document we have today for Egyptian mathematics. We get a good overview of what types of problems the Egyptians would have dealt with in their mathematics. We also get explicitly stated how multiplications and divisions were carried out.
The papyri show how to multiply 2 large numbers together. But to illustrate the method, let's take 2 smaller numbers. Let's do 3 times 6. The scribe would take the first number 3 and put it in one column. In the second column, he would place the number 1. Then he would double the numbers in each column. So 3 becomes 6, and 6 will become 12. And then in the second column, 1 would become 2, and 2 becomes 4. Now here's the really clever bit. The scribe wants to multiply 3 by 6. So he takes the powers of 2 in the second column, which add up to 6. So that's 2 plus 4. Then he moves back to the first column and just takes those rows corresponding to the 2 and the 4. So that's 6 and the 12. He adds those together to get the answer of 18. But for me, the most striking thing about this method is that the scribe has effectively written that second number in binary. 6 is 1 lot of 4, 1 lot of 2, and no units, which is 1, 1, 0. The Egyptians have understood the power of binary over 3,000 years before the mathematician and philosopher Leibniz would reveal their potential. Today, the whole technological world depends on the same principles that were used in ancient Egypt.
The Rhind papyrus was recorded by a scribe called Ahmes around 1650 BC, and its problems are concerned with finding solutions to everyday situations. Several of the problems mention bread and beer, which isn't surprising as Egyptian workers were paid in food and drink. One is concerned with how to divide 9 loaves equally between 10 people without a fight breaking out.
I've got 9 loaves of bread here. I'm going to take 5 of them and cut them into halves.
Of course, 9 people could shave a 10th off their loaf and give the pile of crumbs to the 10th person. But the Egyptians developed a far more elegant solution.
Take the next 4 and divide those into thirds. But 2 of the thirds I'm now going to cut into fifths, so each piece will be 1/15. Each person then gets 1/2, and 1/3, and 1/15. It's through such seemingly practical problems that we start to see a more abstract mathematics developing. Suddenly new numbers are on the scene, fractions, and it isn't too long before the Egyptians are exploring the mathematics of these numbers.
Fractions are clearly of practical importance to anyone dividing quantities for trade in the market. To log these transactions, the Egyptians developed notation which recorded these new numbers. One of the earliest representations of these fractions came from a hieroglyph which had great mystical significance. It's called the Eye of Horus. Horus was an Old Kingdom god, depicted as half man, half falcon.
According to legend, Horus's father was killed by his other son, Seth. Horus was determined to avenge the murder. During one particularly fierce battle, Seth ripped out Horus's eye, tore it up, and scattered it over Egypt. But the gods were looking favourably on Horus. They gathered up the scattered pieces and reassembled the eye.
Each part of the eye represented a different fraction, each one half the fraction before. Although the original eye represented a whole unit, the reassembled eye is 1/64 short. Although the Egyptians stopped at 1/64, implicit in this picture is the possibility of adding more fractions, halving them each time, the sum getting closer and closer to 1, but never quite reaching it. This is the first hint of something called a geometric series, and it appears at a number of points in the Rhind papyrus. But the concept of infinite series would remain hidden until the mathematicians of Asia discovered it centuries later. Having worked out a system of numbers, including these new fractions, it was time for the Egyptians to apply their knowledge to understanding shapes that they encountered day to day. These shapes were rarely regular squares or rectangles, and in the Rhind papyrus we find the area of a more organic form, the circle.
What is astounding in the calculation of the area of a circle is its exactness, really. How they would have found their method is open to speculation, because the texts we have do not show us the methods how they were found.
This calculation is particularly striking because it depends on seeing how the shape of the circle can be approximated by shapes that the Egyptians already understood. The Rhind papyrus states that a circular field with a diameter of 9 units is close in area to a square with sides of 8. But how would this relationship have been discovered? My favourite theory sees the answer in the ancient game of Mancala. Mancala boards were found carved on the roofs of temples. Each player starts with an equal number of stones, and the object of the game is to move them around the board, capturing your opponent's counters on the way.
As the players sat around waiting to make their next move, perhaps one of them realised that sometimes the balls fill the circular holes of the Mancala board in a rather nice way. He might have gone on to experiment with trying to make larger circles.
Perhaps he noticed that 64 stones, the square of 8, can be used to make a circle with diameter 9 stones. By rearranging the stones, the circle has been approximated by a square. And because the area of a circle is pi times the radius squared, the Egyptian calculation gives us the first accurate value for pi.
The area of the circle is 64. Divide this by the radius squared, in this case 4.5 squared, and you get a value for pi. So 64 divided by 4.5 squared is 3.16, just a little under 2/100ths away from its true value. But the really brilliant thing is the Egyptians are using these smaller shapes to capture the larger shape.
But there's one imposing and majestic symbol of Egyptian mathematics we haven't attempted to unravel yet: the pyramid. I've seen so many pictures that I couldn't believe I'd be impressed by them. But meeting them face to face, you understand why they're called one of the 7 wonders of the ancient world. They're simply breathtaking. And how much more impressive they must have been in their day, when the sides were as smooth as glass, reflecting the desert sun.
To me, it looks like there might be mirror pyramids hiding underneath the desert, which will complete these shapes to make perfectly symmetrical octahedrons. Sometimes, in the shimmer of the desert heat, you can almost see these shapes.
It's the hint of symmetry hidden inside these shapes that makes them so impressive for a mathematician. The pyramids are just a little short to create these perfect shapes. But some have suggested that another important mathematical concept might be hidden inside the proportions of the Great Pyramid: the golden ratio. Two lengths are in the golden ratio if the relationship of the longest to the shortest is the same as the sum of the two to the longest side. Such a ratio has been associated with the perfect proportions one finds all over the natural world, as well as in the work of artists, architects and designers for millennia. Whether the architects of the pyramids were conscious of this important mathematical idea, or were instinctively drawn to it because of its satisfying aesthetic properties, we'll never know. For me, the most impressive thing about the pyramids is the mathematical brilliance that went into making them, including the first inkling of one of the great theorems of the ancient world, Pythagoras' theorem.
In order to get perfect right-angled corners on their buildings and pyramids, the Egyptians would have used a rope with knots tied in it. At some point, the Egyptians realised that if they took a triangle with sides marked with 3 knots, 4 knots and 5 knots, it guaranteed them a perfect right angle. This is because 3 squared plus 4 squared is equal to 5 squared. So we've got a perfect Pythagorean triangle. In fact, any triangle whose sides satisfy this relationship will give me a 90-degree angle. But I'm pretty sure that the Egyptians hadn't got this sweeping generalization of their 3-4-5 triangle.
We would not expect to find a general proof because this is not the style of Egyptian mathematics. Every problem was solved using concrete numbers, and then if a verification would be carried out at the end, it would use the result and these concrete given numbers. There's no general proof within the Egyptian mathematical texts.
It would be some 2,000 years before the Greeks and Pythagoras would prove that all right-angled triangles shared certain properties. This wasn't the only mathematical idea that the Egyptians would anticipate. In a 4,000-year-old document called the Moscow Papyrus, we find a formula for the volume of a pyramid with its peak sliced off, which shows the first hint of calculus at work.
For a culture like Egypt that is famous for its pyramids, you would expect problems like this to have been a regular feature within their mathematical texts. The calculation of the volume of a truncated pyramid is one of the most advanced bits, according to our modern standards of mathematics, that we have from ancient Egypt.
The architects and engineers would certainly have wanted such a formula to calculate the amount of materials required to build it. But it's a mark of the sophistication of Egyptian mathematics that they were able to produce such a beautiful method. To understand how they derived their formula, start with a pyramid built such that the highest point sits directly over one corner. 3 of these can be put together to make a rectangular box, so the volume of the skewed pyramid is 1/3 the volume of the box. That is, the height times the length times the width divided by 3. Now comes an argument which shows the very first hints of the calculus at work, thousands of years before Gottfried Leibniz and Isaac Newton would come up with the theory. Suppose you could cut the pyramid into slices. You could then slide the layers across to make the more symmetrical pyramid you see in Giza. However, the volume of the pyramid has not changed, despite the rearrangement of the layers, so the same formula works. The Egyptians were amazing innovators, and their ability to generate new mathematics was staggering. For me, they revealed the power of geometry and numbers, and made the first moves towards some of the exciting mathematical discoveries to come. But there was another civilization that had mathematics to rival that of Egypt, and we know much more about their achievements. This is Damascus, over 5,000 years old and still vibrant and bustling today. It used to be the most important point on the trade routes linking old Mesopotamia with Egypt. The Babylonians controlled much of modern-day Iraq, Iran and Syria from 1800 BC. In order to expand and run their empire, they became masters of managing and manipulating numbers.
We have law codes, for instance, that tell us about the way society is ordered. Now, the people we know most about are the scribes, the professionally literate and numerate people who kept the records for the wealthy families and for the temples and palaces.
Scribe schools existed from around 2500 BC. Aspiring scribes were sent there as children and learned how to read, write, and work with numbers. Scribe records were kept on clay tablets, which allowed the Babylonians to manage and advance their empire. However, many of the tablets we have today aren't official documents, but children's exercises. It's these unlikely relics that give us a rare insight into how the Babylonians approached mathematics.
So this is a geometrical textbook from about the 18th century BC, and I hope you can see that there are lots of pictures on it, and underneath each picture is a text that sets a problem about the picture. So, for instance, this one here says, I drew a square 60 units long, and inside it I drew 4 circles. What are their areas? So this little tablet here was written 1,000 years at least later than the tablet here, but it has a very interesting relationship to it. It also has 4 circles on in a square, roughly drawn, but this isn't a textbook, it's a school exercise, so that the adult scribe who's teaching the student is being given this as an example of completed homework or something like that.
Like the Egyptians, the Babylonians appeared interested in solving practical problems to do with measuring and weighing. The Babylonian solutions to these problems are written like mathematical recipes. A scribe would simply follow and record a set of instructions to get a result. Here's an example of a kind of problem they'd solve.
Now I've got a bundle of cinnamon sticks here, but I'm not going to weigh them. Instead, I'm going to take 4 times their weight and add them to the scales. Now I'm going to add 20 gin. Gin was the ancient Babylonian measure of weight. I'm going to take half of everything here and add it again. So that's 2 bundles and 10 gin. Now everything on this side is equal to 1 manna. 1 manna was 60 gin. And here we have one of the first mathematical equations in history. Everything on this side is equal to 1 manna. But how much does the bundle of cinnamon sticks weigh? Without any algebraic language, they were able to manipulate the quantities to be able to prove that the cinnamon sticks weighed 5 gin. In my mind, it's this kind of problem which gives mathematics a bit of a bad name. You can blame those ancient Babylonians for all those tortuous problems you had at school. But the ancient Babylonian scribes excelled at this kind of problem.
Intriguingly, they weren't using powers of 10 like the Egyptians. They were using powers of 60.
The Babylonians invented their number system, like the Egyptians, by using their fingers. But instead of counting through the 10 fingers on their hand, Babylonians found a much more intriguing way to count body parts. They used the 12 knuckles on one hand and the 5 fingers on the other to be able to count 12 times 5, i.e. 60 different numbers. So for example, this number would have been 2 lots of 12, 24, and then 1, 2, 3, 4, 5 to make 29.
But the number 60 had another powerful property. It can be perfectly divided in a multitude of ways. Here are 60 beans. I can arrange them in 2 rows of 30. 3 rows of 20. 4 rows of 15, 5 rows of 12, or 6 rows of 10. The divisibility of 60 makes it a perfect base in which to do arithmetic. The base 60 system was so successful, we still use elements of it today. Every time we want to tell the time, we recognize units of 60, 60 seconds in a minute, 60 minutes in an hour. But the most important feature of the Babylonians' number system was that it recognized place value. Just as our decimal numbers count how many lots of tens, hundreds and thousands you're recording, the position of each Babylonian number records the power of 60 you're counting.
instead of inventing new symbols for bigger and bigger numbers, they would write 111, so this number would be 3,661. The catalyst for this discovery was the Babylonians' desire to chart the course of the night sky.
The Babylonians' calendar was based on the cycles of the moon, and so they needed a way of recording astronomically large numbers. Month by month, year by year, these cycles were recorded. From about 800 BC, there were complete lists of lunar eclipses.
The Babylonian system of measurement was quite sophisticated at that time. They had a system of angular measurement, 360 degrees in a full circle. Each degree was divided into 60 minutes. A minute was further divided into 60 seconds. So they had a regular system for measurement, and it was in perfect harmony with their number system. So it's well suited not only for observation, but also for calculation.
But in order to calculate and cope with these large numbers, the Babylonians needed to invent a new symbol. And in so doing, they prepared the ground for one of the great breakthroughs in the history of mathematics: zero.
In the early days, the Babylonians, in order to mark an empty place in the middle of a number, would simply leave a blank space. So they needed a way of representing nothing in the middle of a number. So they used a sign as a sort of breathing mark or a punctuation mark, and it comes to mean zero in the middle of a number.
This was the first time zero in any form had appeared in the mathematical universe. But it'd be over 1,000 years before this little placeholder would become a number in its own right. Having established such a sophisticated system of numbers, they harnessed it to tame the arid and inhospitable land that ran through Mesopotamia. Babylonian engineers and surveyors found ingenious ways of accessing water and channeling it to the crop fields. Yet again, they used mathematics to come up with solutions. The Orontes Valley in Syria is still an agricultural hub, and the old methods of irrigation are being exploited today just as they were thousands of years ago. Many of the problems in Babylonian mathematics are concerned with measuring land, and it's here we see for the first time the use of quadratic equations, one of the greatest legacies of Babylonian mathematics.
Quadratic equations involve things where the unknown quantity you're trying to identify is multiplied by itself. We call this squaring because it gives the area of a square. And it's in the context of calculating the area of land that these quadratic equations naturally arise. Here's a typical problem. If a field has an area of 55 units, and one side is 6 units longer than the other, how long is the shorter side? The Babylonian solution was to reconfigure the field as a square. Cut 3 units off the end, and move this round. Now, there's a 3 by 3 piece missing, so let's add this in. The area of the field has increased by 9 units. This makes the new area 64, so the size of the square are 8 units. The problem solver knows that they've added 3 to this side, so the original length must be 5. It may not look like it, but this is one of the first quadratic equations in history.
In modern mathematics, I would use the symbolic language of algebra to solve this problem. But the amazing feat of the Babylonians is that they were using these geometric games to find the value, without any recourse to symbols or formulas. The Babylonians were enjoying problem solving for its own sake. They were falling in love with mathematics.
The Babylonians' fascination with numbers soon found a place in their leisure time too. They were avid game players, The Babylonians and their descendants have been playing a version of backgammon for over 5,000 years.
So the Babylonians played board games, from very posh board games in royal tombs to little bits of board games found in schools, to board games scratched on the entrances of palaces, so that the guardsmen must have played at times when they were bored. And they used dice to move their counters round. People who played games were using numbers in their leisure time to try and outwit their opponent, doing mental arithmetic very fast. And so they were calculating in their leisure time without even thinking about it as being mathematical hard work.
Now's my chance.
I hadn't played backgammon for ages, but I reckon my maths would be good enough to give me a fighting chance.
So it's up to you.
So 6, and I need to move something, so...
But it wasn't as easy as I thought.
Okay.
What the hell is that?
Yeah, this is...
1, this is 2. Now you are in trouble.
So I can't move anything, can I? I can't move these anyway.
You cannot move these. You're gonna
I've just
play
got to...
all
Oh, gosh.
Exactly. There you go.
You seem to be...
3 and 4. So
Just like the ancient Babylonians, my opponents were masters of tactical mathematics.
Yeah. Put it there.
here you
All
go.
right, good game.
The Babylonians are recognized as one of the first cultures to use symmetrical mathematical shapes to make dice. But there is more heated debate about whether they might also have been the first to discover the secrets of another important shape, the right-angled triangle. We've already seen how the Egyptians used a 3-4-5 right-angled triangle. But what the Babylonians knew about this shape, and others like it, is much more sophisticated. This is the most famous and controversial ancient tablet we have. It's called Plimpton 322. Many mathematicians are convinced it shows the Babylonians could well have known the principle regarding right-angled triangles, that the square on the diagonal is the sum of the squares on the sides, and known it centuries before the Greeks claimed it.
This is a copy of the arguably most famous Babylonian tablet, which is Plimpton 322. And these numbers here reflect the width or height of a triangle, this being the diagonal. The other side would be over here, and the square of this column plus the square of the number in this column equals the square of the diagonal. They are arranged in an order of steadily decreasing angle on a very uniform basis, showing that somebody had a lot of understanding of how the numbers fit together.
Here were 15 perfect Pythagorean triangles, all of whose sides had whole number lengths. It's tempting to think that the Babylonians were the first custodians of Pythagoras' theorem, and it's a conclusion that generations of historians have been seduced by.
But there could be a much simpler explanation for the sets of 3 numbers which fulfill Pythagoras' theorem.
It's not a systematic explanation of Pythagorean triples. It's simply a mathematics teacher doing some quite complicated calculations, but in order to produce some very simple numbers in order to set his students problems about right-angled triangles. And in that sense, it's about Pythagorean triples, only incidentally.
The most valuable clues to what they understood could lie elsewhere. This small school exercise tablet is nearly 4,000 years old and reveals just what the Babylonians did know about right-angled triangles. It uses the principle of Pythagoras' theorem to find the value of an astounding new number.
Drawn along the diagonal is a really very good approximation to the square root of 2. And so that shows us that it was known and used in school environments. Now, why is this important? It's because the square root of 2 is what we now call an irrational number. That is, if we write it out in decimals or even in sexagesimal places, it doesn't end. The numbers go on forever after the decimal point.
The implications of this calculation are far-reaching. Firstly, it means the Babylonians knew something of Pythagoras' theorem 1,000 years before Pythagoras. Secondly, the fact that they can calculate this number to an accuracy of 4 decimal places shows an amazing arithmetic facility, as well as a passion for mathematical detail.
The Babylonians' mathematical dexterity was astounding, and for nearly 2,000 years they spearheaded intellectual progress in the ancient world. But when their imperial power began to wane, so did their intellectual vigour. By 330 BC, the Greeks had advanced their imperial reach into old Mesopotamia. This is Palmyra in central Syria, a once great city built by the Greeks. The mathematical expertise needed to build structures with such geometric perfection is impressive. Just like the Babylonians before them, the Greeks were passionate about mathematics.
The Greeks were clever colonists. They took the best from the civilizations they invaded to advance their own power and influence. But they were soon making contributions themselves. In my opinion, their greatest innovation was to do with a shift in the mind. What they initiated would influence humanity for centuries. They gave us the power of proof.
Somehow they decided that they had to have a deductive system for their mathematics. And the typical deductive system was to begin with certain axioms which you assume are true. It's as if you assume a certain theorem is true without proving it. And then using logical methods and very careful steps, from these axioms you prove theorems. And then from those theorems you prove more theorems. And it just snowballs that way.
Proof is what gives mathematics its strength. It's the power of proof, which means that the discoveries of the Greeks are as true today as they were 2,000 years ago. I needed to head west into the heart of the old Greek Empire to learn more. For me, Greek mathematics has always been heroic and romantic. I'm on my way to Samos, less than a mile from the Turkish coast. This place has become synonymous with the birth of Greek mathematics, and it's down to the legend of one man.
His name is Pythagoras. The legends that surround his life and work have contributed to the celebrity status he has gained over the last 2,000 years. He's credited, rightly or wrongly, with beginning the transformation from mathematics as a tool for accounting to the analytic subject we recognize today.
Pythagoras is a controversial figure. Because he left no mathematical writings, many have questioned whether he indeed solved any of the theorems attributed to him. He founded a school in Samos in the 6th century BC, but his teachings were considered suspect, and the Pythagoreans a bizarre sect.
There is good evidence that there were schools of Pythagoreans. They may have looked more like sects than what we associate with philosophical schools, because they didn't just share knowledge, they also shared a way of life. They may have been communal living, and they all seem to have been involved in the politics of their cities. One feature that makes them unusual in the ancient world is that they included women.
But Pythagoras is synonymous with understanding something that eluded the Egyptians and the Babylonians: the properties of right-angled triangles. What's known as Pythagoras' theorem states that if you take any right-angled triangle, build squares on all the sides, then the area of the largest square is equal to the sum of the squares on the two smaller sides.
It's at this point for me that mathematics is born, and a gulf opens up between the other sciences.
And the proof is as simple as it is devastating in its implications.
Place 4 copies of the right-angled triangle on top of this surface.
The square that you now see has sides equal to the hypotenuse of the triangle. By sliding these triangles around, we see how we can break the area of the large square up into the sum of two smaller squares, whose sides are given by the two short sides of the triangle. In other words, the square on the hypotenuse is equal to the sum of the squares on the other sides. Pythagoras' theorem. It illustrates one of the characteristic themes of Greek mathematics, the appeal to beautiful arguments in geometry, rather than a reliance on number.
Pythagoras may have fallen out of favour, and many of the discoveries accredited to him have been contested recently. But there's one mathematical theory that I'm loath to take away from him. It's to do with music and the discovery of the harmonic series.
The story goes that walking past a blacksmith one day, Pythagoras heard anvils being struck and noticed how the notes being produced sounded in perfect harmony. He believed that there must be some rational explanation to make sense of why the notes sounded so appealing. The answer was mathematics. Experimenting with a stringed instrument, Pythagoras discovered that the intervals between harmonious musical notes were always represented as whole number ratios. And here's how he might have constructed his theory.
First, play a note on the open string. Next, take half the length. The note almost sounds the same as the first note. In fact, it's an octave higher, but the relationship is so strong we give these notes the same name. Now, take a third the length. We get another note which sounds harmonious next to the first two. But take a length of string which is not in a whole number ratio, and all we get is dissonance.
According to legend, Pythagoras was so excited by this discovery that he concluded the whole universe was built from numbers. But he and his followers were in for a rather unsettling challenge to their worldview. And it came about as a result of the theorem which bears Pythagoras' name. Legend has it, one of his followers, a mathematician called Hippasus, set out to find the length of the diagonal for a right-angled triangle with two sides measuring 1 unit. Pythagoras' theorem implied that the length of the diagonal was a number whose square was 2. The Pythagoreans assumed that the answer would be a fraction. But when Hippasus tried to express it in this way, no matter how he tried, he couldn't capture it. Eventually, he realized his mistake. It was the assumption that the value was a fraction at all which was wrong. The value of the square root of 2 was the number that the Babylonians etched into the Yale tablet. However, they didn't recognize the special character of this number, but Hippasus did. It was an irrational number.
The discovery of this new number, and others like it, is akin to an explorer discovering a new continent, or a naturalist finding a new species. But these irrational numbers didn't fit the Pythagorean worldview. Later Greek commentators tell the story of how Pythagoras swore his sect to secrecy, but Hippasus let slip the discovery and was promptly drowned for his attempts to broadcast their research.
But these mathematical discoveries could not be easily suppressed. Schools of philosophy and science started to flourish all over Greece, building on these foundations. The most famous of these was the Academy. Plato founded this school in Athens in 387 BC. Although we think of him today as a philosopher, he was one of mathematics' most important patrons. Plato was enraptured by the Pythagorean worldview and considered mathematics the bedrock of knowledge.
Some people would say that Plato is possibly the most influential figure for our perception of Greek mathematics. He argued that mathematics is an important form of knowledge and does have a connection with reality. So by knowing mathematics, we'll know more about reality.
In his dialogue Timaeus, Plato proposes the thesis that geometry is the key to unlocking the secrets of the universe, a view still held by scientists today. Indeed, the importance Plato attached to geometry is encapsulated in the sign that was mounted above the academy. Let no one ignorant of geometry enter here. Plato proposed that the universe could be crystallized into 5 regular symmetrical shapes. These shapes, which we now call the Platonic solids, were composed of regular polygons assembled to create 3-dimensional symmetrical objects. The tetrahedron represented fire. The icosahedron, made from 20 triangles, represented water. The stable cube was earth. The 8-faced octahedron was air. And the 5th Platonic solid, the dodecahedron, made out of 12 pentagons, was reserved for the shape which captured Plato's view of the universe. Plato's theory would have a seismic influence and continue to inspire mathematicians and astronomers
for over 1,500 years. In addition to the breakthroughs made in the academy, mathematical triumphs were also emerging from the edge of the Greek Empire, and owed as much to the mathematical heritage of the Egyptians as the Greeks. Alexandria became a hub of academic excellence under the rule of the Ptolemies in the 3rd century BC, and its famous library soon gained a reputation to rival Plato's academy.
The kings of Alexandria were prepared to invest in the arts, in culture, in technology, mathematics, grammar, because patronage for cultural pursuits was one way of showing that you were a more prestigious ruler and had a better entitlement to greatness.
The old library and its precious contents were destroyed when the Muslims conquered Egypt in the 7th century. But its spirit is alive in a new building. Today, the library remains a place of discovery and scholarship. Mathematicians and philosophers flocked to Alexandria, driven by their thirst for knowledge and the pursuit of excellence. The patrons of the library were the first professional scientists, individuals who were paid for their devotion to research. But of all those early pioneers, my hero is the enigmatic Greek mathematician Euclid. We know very little about Euclid's life, but his greatest achievements were as a chronicler of mathematics. Around 300 BC, he wrote the most important textbook of all time, the Elements. In the Elements, we find the culmination of the mathematical revolution which had taken place in Greece. It's built on a series of mathematical assumptions called axioms. For example, a line can be drawn between any 2 points. From these axioms, logical deductions are made and mathematical theorems established. The Elements contains formulas for calculating the volumes of cones and cylinders, proofs about geometric series, perfect numbers, and primes. The climax of the Elements is a proof that there are only 5 Platonic solids. For me, this last theorem captures the power of mathematics.
It's one thing to build 5 symmetrical solids, quite another to come up with a watertight, logical argument for why there can't be a 6th. The Elements unfolds like a wonderful, logical mystery novel. But this is a story which transcends time. Scientific theories get knocked down from one generation to the next. But the theorems in the Elements are as true today as they were 2,000 years ago.
When you stop and think about it, it's really amazing that it's the same theorems that we teach. We may teach them in a slightly different way, or we may organize them differently, but it's Euclidean geometry that is still valid, and even in higher mathematics. When you go to higher dimensional spaces, you're still using Euclidean geometry.
Alexandria must have been an inspiring place for the ancient scholars, and Euclid's fame would have attracted even more eager young intellectuals to the Egyptian port. One mathematician who particularly enjoyed the intellectual environment in Alexandria was Archimedes.
He would become a mathematical visionary.
The best Greek mathematicians, they were always pushing the limits, pushing the envelope. So Archimedes did what he could with polygons, with solids. He then moved on to centers of gravity, or he then moved on to the spiral. This instinct to try and mathematize everything is something that I see as a legacy.
One of Archimedes' specialities was weapons of mass destruction. They were used against the Romans when they invaded his home of Syracuse in 212 BC. He also designed mirrors which harnessed the power of the sun to set the Roman ships on fire. But to Archimedes, these endeavours were mere amusements in geometry. He had loftier ambitions.
Archimedes was enraptured by pure mathematics and believed in studying mathematics for its own sake, and not for the ignoble trade of engineering or the sordid quest for profit.
One of his finest investigations into pure mathematics was to produce formulas to calculate the areas of regular shapes.
Archimedes' method was to capture new shapes by using shapes he already understood. So, for example, to calculate the area of a circle, he would enclose it inside a triangle. And then by doubling the number of sides on the triangle, the enclosing shape would get closer and closer to the circle. Indeed, we sometimes call a circle a polygon with an infinite number of sides. But by estimating the area of the circle, Archimedes is in fact getting a value for pi, the most important number in mathematics.
However, it was calculating the volumes of solid objects where Archimedes excelled. He found a way to calculate the volume of a sphere by slicing it up and approximating each slice as a cylinder. He then added up the volumes of the slices to get an approximate value for the sphere. But his act of genius was to see what happens if you make the slices thinner and thinner. In the limit, the approximation becomes an exact calculation. But it was Archimedes' commitment to mathematics that would be his undoing.
Archimedes was contemplating a problem about circles traced in the sand when a Roman soldier accosted him. Archimedes was so engrossed in his problem that he insisted he'd be allowed to finish his theorem. But the Roman soldier was not interested in Archimedes' problem and killed him on the spot. Even in death, Archimedes' devotion to mathematics was unwavering.
By the middle of the 1st century BC, the Romans had tightened their grip on the old Greek Empire. They were less smitten with the beauty of mathematics and were more concerned with its practical applications. This pragmatic attitude signalled the beginning of the end for the great library of Alexandria. But one mathematician was determined to keep the legacy of the Greeks alive. Hypatia was exceptional, a female mathematician, and a pagan in the piously Christian Roman Empire.
Hypatia was very prestigious and very influential in her time. She was a teacher with a lot of students, a lot of followers. She was politically influential in Alexandria. So it's this combination of high knowledge and high prestige that may have made her a figure of hatred for the Christian mob.
One morning during Lent, Hypatia was dragged off her chariot by a zealous Christian mob and taken to a church. There she was tortured and brutally murdered. The dramatic circumstances of her life and death fascinated later generations. Sadly, her cult status eclipsed her mathematical achievements. She was in fact a brilliant teacher and theorist, and her death dealt a final blow to the Greek mathematical heritage of Alexandria. My travels have taken me on a fascinating journey to uncover the passion and innovation of the world's earliest mathematicians. It's the breakthroughs made by those early pioneers of Egypt, Babylon and Greece that are the foundations on which my subject is built today. But this is just the beginning of my mathematical odyssey. The next leg of my journey lies east in the depths of Asia, where mathematicians scaled even greater heights in pursuit of knowledge. With this new era came a new language of algebra and numbers, better suited to telling the next chapter in the story of maths. The Great Wall of China stretches for thousands of miles. Nearly 2,000 years in the making, this vast defensive wall was begun in 220 BC to protect China's growing empire.
The Great Wall of China is an amazing feat of engineering, built over rough and high countryside. As soon as they started building, the ancient Chinese realized they had to make calculations about distances, angles of elevation, and amounts of material. So perhaps it isn't surprising that this inspired some very clever mathematics to help build Imperial China.
At the heart of ancient Chinese mathematics was an incredibly simple number system, which laid the foundations for the way we count in the West today. When a mathematician wanted to do a sum, he would use small bamboo rods. These rods were arranged to represent the numbers 1 to 9. They were then placed in columns, each column representing units, tens, hundreds, thousands, and so on. So the number 924 was represented by putting the symbol 4 in the units column, the symbol 2 in the tens column, and the symbol 9 in the hundreds column. 924.
This is what we call a decimal place value system, and it's very similar to the one we use today. We too use numbers from 1 to 9, and we use their position to indicate whether it's units, tens, hundreds or thousands. But the power of these rods is that it makes calculations very quick. In fact, the way the ancient Chinese did their calculations is very similar to the way we learn today in school.
Not only were the ancient Chinese the first to use a decimal place value system, but they did so over 1,000 years before we adopted it in the West. But they only used it when calculating with the rods. When writing the numbers down, the ancient Chinese didn't use the place value system. Instead, they used a far more laborious method, in which special symbols stood for tens, hundreds, thousands, and so on. So the number 924 will be written out as 9 hundreds, 2 tens, and 4. Not quite so efficient.
You see, the problem was that the ancient Chinese didn't have a concept of zero. They didn't have a symbol for zero. It just didn't exist as a number. Using the counting rods, they would use a blank space, where today we would write a 0. The problem came with trying to write down this number, which is why they had to create these new symbols for tens, hundreds and thousands. Without a 0, the written number was extremely limited.
But the absence of 0 didn't stop the ancient Chinese from making giant mathematical steps. In fact, there was a widespread fascination with number in ancient China. According to legend, the first sovereign of China, the Yellow Emperor, had one of his deities create mathematics in 2800 BC, believing that number held cosmic significance. And to this day, the Chinese still believe in the mystical power of numbers. Odd numbers are seen as male, even numbers female. The number 4 is to be avoided at all costs.
The number 8 brings good fortune. And the ancient Chinese were drawn to patterns in numbers, developing their own, rather early version of Sudoku. It was called the Magic Square. Legend has it that thousands of years ago, Emperor Yu was visited by a sacred turtle that came out of the depths of the Yellow River. On its back were numbers arranged into a magic square, a little like this. In this square, which was regarded as having great religious significance, all the numbers in each line, horizontal, vertical, and diagonal, all add up to the same number, 15. Now, the magic square may be no more than a fun puzzle, but it shows the ancient Chinese fascination with mathematical patterns. And it wasn't too long before they were creating even bigger magic squares, with even greater magical and mathematical powers. But mathematics also played a vital role in the running of the emperor's court. The calendar and the movement of the planets were of the utmost importance to the emperor, influencing all his decisions, even down to the way his day was planned. So astronomers became prize members of the imperial court, and astronomers were always mathematicians. Everything in the emperor's life was governed by the calendar, and he ran his affairs with mathematical precision. The emperor even got his mathematical advisors to come up with a system to help him sleep his way through the vast number of women he had in his harem. Never one to miss a trick, the mathematical advisors decided to base the harem on a mathematical idea called a geometric progression. Maths has never had such a fun purpose.
Legend has it that in the space of 15 nights, the emperor had to sleep with 121 women. The empress, 3 senior consorts, 9 wives, 27 concubines, and 81 slaves. The mathematicians would soon have realised that this was a geometric progression, a series of numbers in which you get from one number to the next by multiplying by the same number each time, in this case 3. Each group of women is 3 times as large as the previous group. So the mathematicians could quickly draw up a rota to ensure that in the space of 15 nights, the emperor slept with every woman in the harem. The first night was reserved for the empress. The next was for the 3 senior consorts. The 9 wives came next. And then the 27 concubines were chosen in rotation, 9 each night. And then finally, over a period of 9 nights, the 81 slaves were dealt with in groups of 9.
Being the emperor certainly required stamina, a bit like being a mathematician. But the object is clear: to procure the best possible imperial succession. The rota ensured that the emperor slept with the ladies of highest rank closest to the full moon, when their yin, their female force, would be at its highest and be able to match his yang, or male force.
The emperor's court wasn't alone in its dependence on mathematics. It was central to the running of the state. Ancient China was a vast and growing empire, with a strict legal code, widespread taxation, and a standardized system of weights, measures, and money. The empire needed a highly trained civil service, competent in mathematics. And to educate these civil servants was a mathematical textbook, probably written in around 200 BC, the 9 chapters. The book is a compilation of 246 problems in practical areas such as trade, payment of wages, and taxes. And at the heart of these problems lies one of the central themes of mathematics: how to solve equations. Equations are a little bit like cryptic crosswords. You're given a certain amount of information about some unknown numbers, and from that information you've got to deduce what the unknown numbers are. For example, with my weights and scales, I found out that 1 plum, together with 3 peaches, weighs a total of 15 grams. But 2 plums, together with 1 peach, weighs a total of 10 grams. From this information, I can deduce what a single plum weighs and a single peach weighs, and this is how I do it. If I take the first set of scales, 1 plum and 3 peaches weighing 15 grams, and double it, I get 2 plums and 6 peaches weighing 30 grams. If I take this and subtract from it the second set of scales, that's 2 plums and a peach weighing 10 grams, I'm left with an interesting result: no plums. Having eliminated the plums, I've discovered that 5 peaches weighs 20 grams. So, a single peach weighs 4 grams. And from this, I can deduce that the plum weighs 3 grams. The ancient Chinese went on to apply similar methods to larger and larger numbers of unknowns, using it to solve increasingly complicated equations. What's extraordinary is that this particular system of solving equations didn't appear in the West until the beginning of the 19th century. In 1809, while analysing a rock called Pallas in the asteroid belt, Carl Friedrich Gauss, who would become known as the Prince of Mathematics, rediscovered this method, which had been formulated in ancient China centuries earlier. Once again, ancient China streets ahead of Europe. But the Chinese were to go on to solve even more complicated equations, involving far larger numbers. In what's become known as the Chinese remainder theorem, the Chinese came up with a new kind of problem. In this, we know the number that's left when the unknown number in the equation is divided by a given number, say 3, 5 or 7. Of course, this is a fairly abstract mathematical problem, but the ancient Chinese still managed to couch it in practical terms. So, a woman in the market has a tray of eggs, but she doesn't know how many eggs she's got. What she does know is that if she arranges them in threes, she has 1 egg left over. If she arranges them in fives, she gets 2 eggs left over. But if she arranged them in rows of 7, she found she had 3 eggs left over. The ancient Chinese found a systematic way to calculate that the smallest number of eggs she could have had in the tray is 52. But the more amazing thing is that you can capture such a large number like 52 by using these small numbers like 3, 5 and 7. This way of looking at numbers would become a dominant theme in mathematics over the last 2 centuries. By the 6th century AD, the Chinese remainder theorem was being used in ancient Chinese astronomy to measure planetary movement. But today it still has practical uses. Internet cryptography encodes numbers using mathematics that has its origins in the Chinese remainder theorem. By the 13th century, mathematics was a long-established part of the curriculum, with over 30 mathematics schools scattered across the country. The golden age of Chinese maths had arrived. And its most important mathematician was called Qin Zhu Shao. Legend has it that Qin Zhu Shao was something of a scoundrel. He was a fantastically corrupt imperial administrator who crisscrossed China, lurching from one post to another. Repeatedly sacked for embezzling government money, he poisoned anyone who got in his way. Qin Zhu Shao was reputedly described as violent as a tiger or a wolf, and as poisonous as a scorpion or a viper. So, not surprisingly, he made a fierce warrior. For 10 years he fought against the invading Mongols, but for much of that time he was complaining that his military life took him away from his true passion. No, not corruption, but mathematics. Qin started trying to solve equations that grew out of trying to measure the world around us. Quadratic equations involve numbers that are squared, or to the power of 2, say 5 times 5. The ancient Mesopotamians had already realized that these equations were perfect for measuring flat, two-dimensional shapes, like Tiananmen Square. But Qin was interested in more complicated equations, cubic equations. These involve numbers which are cubed, or to the power of 3, say 5 times 5 times 5. And they were perfect for capturing three-dimensional shapes, like Chairman Mao's mausoleum. Qin found a way of solving cubic equations, and this is how it worked. Say Qin wants to know the exact dimensions of Chairman Mao's mausoleum. He knows the volume of the building and the relationships between the dimensions. In order to get his answer, Qin uses what he knows to produce a cubic equation. He then makes an educated guess at the dimensions. Although he's captured a good proportion of the mausoleum, there are still bits left over. Qin takes these bits and creates a new cubic equation. He can now refine his first guess by trying to find a solution to this new cubic equation, and so on. Each time he does this, the pieces he's left with get smaller and smaller, and his guesses get better and better. What's striking is that Qin's method for solving equations wasn't discovered in the West until the 17th century, when Isaac Newton came up with his own, very similar approximation method. The power of this technique is that it can be applied to even more complicated equations. Qin even used his techniques to solve an equation involving numbers up to the power of 10. This was extraordinary stuff, highly complex mathematics. Now, Qin may have been years ahead of his time, but there was a problem with his technique. It only gave him an approximate solution. Now, that might be good enough for an engineer, but not for a mathematician. Mathematics is an exact science. We like things to be precise. And Qian just couldn't come up with a formula to give him an exact solution to these complicated equations. China had made great mathematical leaps, but the next great mathematical breakthroughs were to happen in a country lying to the southwest of China. A country that had a rich mathematical tradition that would change the face of maths forever.
In the religions of India, the universe was born out of nothingness, and nothingness is the ultimate goal of humanity. So it's perhaps not surprising that a culture that so enthusiastically embraced the void should be happy with the notion of zero.
The Indians even used the word for the philosophical idea of the void, shunya, to represent the new mathematical term zero. In the 7th century, the brilliant Indian mathematician Brahmagupta proved some of the essential properties of zero. Brahmagupta's rules about calculating with zero are taught in schools all over the world to this day. 1 plus 0 equals 1. 1 minus 0 equals 1. 1 times 0 is equal to 0. But Brahmagupta came a cropper when he tried to do 1 divided by 0. After all, what number times 0 equals 1? It would require a new mathematical concept, that of infinity, to make sense of dividing by 0. And the breakthrough was made by a 12th century Indian mathematician called Bhaskara II. And it works like this. If I take a fruit and I divide it into halves, I get 2 pieces. So 1 divided by half is 2. If I divide it into thirds, I get 3 pieces. So when I divide it into smaller and smaller fractions, I get more and more pieces. So ultimately, when I divide by a piece which is of 0 size, I'll have infinitely many pieces. So for Bhaskara, 1 divided by 0 is infinity. But the Indians were to go further in their calculations with 0. For example, if you take 3 from 3 and get 0, what happens when you take 4 from 3? It looks like you have nothing. But the Indians recognized that this was a new sort of nothing, negative numbers. The Indians called them debts because they were perfect for solving equations like, if I have 3 batches of material and take 4 away, how many have I left? This may seem odd and impractical, but that was the beauty of Indian mathematics. Their ability to come up with negative numbers and 0 was because they thought of numbers as abstract entities. They weren't just for counting and measuring pieces of cloth. They had a life of their own, floating free of the real world. This led to an explosion of mathematical ideas. The Indians' abstract approach to mathematics soon revealed a new side to the problem of how to solve quadratic equations. That is, equations including numbers to the power of 2. Brahmagupta's understanding of negative numbers allowed him to see that quadratic equations always have 2 solutions, one of which could be negative.
Brahmagupta went even further, solving quadratic equations with 2 unknowns, a question which wouldn't be considered in the West until 1657, when the French mathematician Fermat challenged his colleagues with the same problem. Little did he know that they'd been beaten to a solution by Brahmagupta 1,000 years earlier.
Brahmagupta was beginning to find abstract ways of solving equations. But astonishingly, he was also developing a new mathematical language to express that abstraction. Brahmagupta was experimenting with ways of writing his equations down, using the initials of the names of different colours to represent unknowns in his equations.
A new mathematical language was coming to life, which would ultimately lead to the X's and Y's which fill today's mathematical journals.
But it wasn't just new notation that was being developed. Indian mathematicians were responsible for making fundamental new discoveries in the theory of trigonometry. The power of trigonometry is that it acts like a dictionary, translating geometry into numbers and back. Although first developed by the ancient Greeks, it was in the hands of the Indian mathematicians that the subject truly flourished. At its heart lies the study of right-angled triangles.
In trigonometry, you can use this angle here to find the ratios of the opposite side to the longest side. There's a function called the sine function, which when you input the angle, outputs the ratio. So for example, in this triangle, the angle is about 30 degrees. So the output of the sine function is a ratio of 1 to 2, telling me that this side is half the length of the longest side.
The sine function enables you to calculate distances when you're not able to make an accurate measurement. To this day, it's used in architecture and engineering,
The Indians used it to survey the land around them, navigate the seas, and ultimately chart the depths of space itself. It was central to the work of observatories like this one in Delhi, where astronomers would study the stars.
The Indian astronomers could use trigonometry to work out the relative distance between the Earth and the Moon and the Earth and the Sun. You can only make the calculation when the Moon is half full, because that's when it's directly opposite the Sun. So the Sun, Moon and Earth create a right-angled triangle.
Now the Indians could measure that the angle between the Sun and the observatory was 1/7 of a degree. The sine function of 1/7 of a degree gives me the ratio of 400 to 1.
This means that the Sun is 400 times further from the Earth than the Moon is. So, using trigonometry, the Indian mathematicians could explore the solar system without ever having to leave the surface of the Earth.
The ancient Greeks had been the first to explore the sine function, listing precise values for some angles. But they couldn't calculate the sines of every angle. The Indians were to go much further, setting themselves a mammoth task. The search was on to find a way to calculate the sine function of any angle you might be given. The breakthrough in the search for the sine function of every angle will be made here in Kerala in South India. In the 15th century, this part of the country became home to one of the most brilliant schools of mathematicians to have ever worked. Their leader was called Madhava, and he was to make some extraordinary mathematical discoveries.
The key to Madhava's success was the concept of the infinite. Madhava discovered that you could add up infinitely many things with dramatic effects. Previous cultures had been nervous of these infinite sums, but Madhava was happy to play with them. For example, here's how 1 can be made up by adding infinitely many fractions.
I'm heading from 0 to 1 on my boat, but I can split my journey up into infinitely many fractions. So I can get to a half. Then I can sail on a quarter, then an eighth, then a 16th, and so on. The smaller the fractions I move, the nearer to 1 I get. But I'll only get there once I've added up infinitely many fractions.
Now, physically and philosophically, it seems rather a challenge to add up infinitely many things. But that's the power of mathematics, to make sense of the impossible. By producing a language to articulate and manipulate the infinite, you can prove that after infinitely many steps, you'll reach your destination.
Such infinite sums are called infinite series, and Madhava was doing a lot of research into the connections between these series and trigonometry. First, he realised that he could use the same principle of adding up infinitely many fractions to capture one of the most important numbers in mathematics, pi. Pi is the ratio of the circle's circumference to its diameter. It's a number that appears in all sorts of mathematics, but is especially useful for engineers because any measurements involving curves soon require pi. So for centuries, mathematicians searched for a precise value for pi.
It was in 6th century India that the mathematician Aryabhata gave a very accurate approximation for pi, namely 3.1416. He went on to use this to make a measurement of the circumference of the Earth, and he got it as 24,835 miles, which amazingly is only 70 miles away from its true value. But it was in Kerala in the 15th century that Madhava realised he could use infinity to get an exact formula for pi. I was taught at university that this formula for pi was discovered by the 17th century German mathematician Leibniz. But amazingly, it was actually discovered here in Kerala 2 centuries earlier by Madhava. He went on to use the same sort of mathematics to get infinite series expressions for the sine formula in trigonometry. And the wonderful thing is that you can use these formulas now to calculate the sine of any angle to any degree of accuracy.
But Eastern mathematics was to have a major impact in Europe, thanks to the development of one of the major powers of the medieval world. In the 7th century, a new empire began to spread across the Middle East. The teachings of the Prophet Muhammad inspired a vast and powerful Islamic empire, which soon stretched from India in the east to here in Morocco in the west. And at the heart of this empire lay a vibrant intellectual culture. A great library and centre of learning was established in Baghdad. Called the House of Wisdom, its teachings spread throughout the Islamic Empire, reaching schools like this one here in Fez. Subjects studied included astronomy, medicine, chemistry, zoology, and mathematics. The Muslim scholars collected and translated many ancient texts, effectively saving them for posterity. In fact, without their intervention, we may never have known about the ancient cultures of Egypt, Babylon, Greece and India. But the scholars at the House of Wisdom weren't content simply with translating other people's mathematics. They wanted to create a mathematics of their own, to push the subject forward. Such intellectual curiosity was actively encouraged in the early centuries of the Islamic Empire. The Quran asserted the importance of knowledge. Learning was nothing less than a requirement of God. In fact, the needs of Islam demanded mathematical skill. The devout needed to calculate the time of prayer and the direction of Mecca to pray towards. And the prohibition of depicting the human form meant that they had to use much more geometric patterns to cover their buildings. In fact, the Muslim artists discovered all the different sorts of symmetry that you can depict on a two-dimensional wall. The director of the House of Wisdom in Baghdad was a Persian scholar called Muhammad al-Khwarizmi. Al-Khwarizmi was an exceptional mathematician who was responsible for introducing 2 key mathematical concepts to the West.
Al-Khwarizmi recognised the incredible potential that the Hindu numerals had to revolutionise mathematics and science. His work explaining the power of these numbers to speed up calculations and do things effectively was so influential that it wasn't long before they were adopted as the numbers of choice amongst the mathematicians of the Islamic world. In fact, these numbers have now become known as the Hindu Arabic numerals.
These numbers, 1 to 9 and 0, are the ones we use today all over the world. But Al-Khwarizmi was to create a whole new mathematical language. It was called algebra and was named after the title of his book, Al-Jabra wa al-Makbal, or calculation by restoration or reduction. Algebra is the grammar that underlies the way that numbers work. It's a language that explains the patterns that lie behind the behaviour of numbers. It's a bit like a code for running a computer program. The code will work whatever the numbers you feed into the program.
For example, mathematicians might have discovered that if you take a number and square it, that's always 1 more than if you take the numbers either side and multiply those together. For example, 5 times 5 is 25, which is 1 more than 4 times 6, 24. 6 times 6 is always 1 more than 5 times 7, and so on.
Khayyam's major mathematical work was devoted to finding the general method to solve all cubic equations. Rather than looking at particular examples, Khayyam carried out a systematic analysis of the problem, true to the algebraic spirit of al-Khwarizmi.
Khayyam's analysis revealed for the first time that there were several different sorts of cubic equation. But what held him back is that he was still very influenced by the geometric heritage of the Greeks. He couldn't separate the algebra from the geometry. In fact, he wouldn't even consider equations in higher degrees, because they described geometric objects in more than 3 dimensions, something he regarded as impossible. Although the geometry allowed him to analyse these cubic equations to some extent, he still couldn't come up with a purely algebraic solution.
It would be another 500 years before mathematicians could make the leap and find a general solution to the cubic equation. And that leap would finally be made in the West, in Italy. During the centuries in which China, India and the Islamic Empire had been in the ascendant, Europe had fallen under the shadow of the Dark Ages. All intellectual life, including the study of mathematics, had stagnated. But by the 13th century, things were beginning to change. Led by Italy, Europe was starting to explore and trade with the East. And with that contact came the spread of Eastern knowledge to the West.
It was the son of a customs official that would become Europe's first great medieval mathematician. As a child, he travelled around North Africa with his father,
where he learnt about the developments of Arabic mathematics, and especially the benefits of the Hindu-Arabic numerals. When he got home to Italy, he wrote a book that would be hugely influential in the development of Western mathematics.
The mathematician was called Leonardo of Pisa, better known as Fibonacci. And in his Book of Calculating, Fibonacci promoted the new number system, demonstrating how simple it was compared to the Roman numerals that were in use across Europe. Calculations were far easier, a fact that had huge consequences for anyone dealing with numbers. Pretty much everyone, from mathematicians to merchants.
But there was widespread suspicion of these new numbers. Old habits die hard, and the authorities just didn't trust them. Some believed that they would be more open to fraud, that you could tamper with them. Others believed that they'd be so easy to use for calculations that it would empower the masses, taking authority away from the intelligentsia, who knew how to use the old sort of numbers.
The city of Florence even banned them in 1299. But over time, common sense prevailed. The new system spread throughout Europe, and the old Roman system slowly became defunct. At last, the Hindu-Arabic numerals 0 to 9 had triumphed.
Today, Fibonacci is best known for the discovery of some numbers now called the Fibonacci sequence. The numbers arose when he was trying to solve a riddle about the mating habit of rabbits. Suppose a farmer has a pair of rabbits. Now, rabbits take 2 months to reach maturity, and after that they give birth to another pair of rabbits each month. So the problem was how to determine how many pairs of rabbits there will be in any given month.
Well, during the first month, you have 1 pair of rabbits. And since they haven't matured, they can't reproduce. During the second month, there's still only 1 pair. But at the beginning of the third month, the first pair reproduces for the first time, so there are 2 pairs of rabbits. At the beginning of the fourth month, The first pair reproduces again, but the second pair is not mature enough, so there are 3 pairs. In the 5th month, the first pair reproduces, and the second pair reproduces for the first time, but the third pair is still too young, so there are 5 pairs. The mating ritual continues. But what you soon realise is the number of pairs of rabbits you have in any given month is the sum of the pairs of rabbits that you've had in each of the 2 previous months. So the sequence goes 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, and so on. The Fibonacci numbers are nature's favourite numbers. It's not just rabbits that use them. If you count the number of petals on a flower, it's invariably a Fibonacci number. You find these numbers running up and down pineapples if you count the number of segments. Even snails use them to grow their shells. Wherever you find growth in nature, you find the Fibonacci numbers. But the next major breakthrough in European mathematics wouldn't happen until the early 16th century. It would involve finding the general method that would solve all cubic equations. And it would happen here in the Italian city of Bologna. The University of Bologna was the crucible of European mathematical thought at the beginning of the 16th century. Pupils from all over Europe flocked here and developed a new form of spectator sport, the mathematical competition. Large audiences would gather to watch mathematicians challenge each other with numbers, a kind of intellectual fencing match. But even in this questioning atmosphere, it was believed that some problems were just unsolvable. It was generally assumed that finding a general method to solve all cubic equations was impossible. But one scholar was to prove everyone wrong. His name was Tartaglia, but he certainly didn't look the heroic architect of a new mathematics. At the age of 12, he'd been slashed across the face with a sabre by a rampaging French army. The result was a terrible facial scar and a devastating speech impediment. In fact, Tartaglia was the nickname he'd been given as a child, and means the stammerer. Shunned by his schoolmates, Tartaglia lost himself in mathematics. And it wasn't long before he'd found the formula to solve one type of cubic equation. But Tartaglia soon discovered that he wasn't the only one to believe he'd cracked the cubic. A young Italian called Fior was boasting that he too held the secret formula for solving cubic equations. When news broke about the discoveries made by the 2 mathematicians, a competition was arranged to pit them against each other. The intellectual fencing match of the century was about to begin. The trouble was that Tartaglia only knew how to solve one sort of cubic equation, and Fior was ready to challenge him with questions about a different sort. But just a few days before the contest, Tartaglia worked out how to solve this different sort, and with this new weapon in his arsenal, he thrashed his opponent, solving all the questions in under 2 hours. Tartaglia went on to find the formula to solve all types of cubic equations. News soon spread, and a mathematician in Milan called Cardano became so desperate to find the solution that he persuaded a reluctant Tartaglia to reveal the secret to him. But on one condition, that Cardano keep the secret and never publish. But Cardano couldn't resist discussing Tartaglia's solution with his brilliant student Ferrari. As Ferrari got to grips with Tartaglia's work, he realised that he could use it to solve the more complicated quartic equation, an amazing achievement. Cardano couldn't deny his student his just rewards, and he broke his vow of secrecy, publishing Tartaglia's work together with Ferrari's brilliant solution of the quartic. Poor Tartaglia never recovered,
and died penniless. And to this day, the formula that solves the cubic equation is known as Cardano's formula. Tartaglia may not have won glory in his lifetime, but his mathematics managed to solve a problem that had bewildered the great mathematicians of China, India, and the Arab world. It was the first great mathematical breakthrough to happen in modern Europe.
The Europeans now had in their hands the new language of algebra, the powerful techniques of the Hindu-Arabic numerals, and the beginnings of the mastery of the infinite. It was time for the Western world to start writing its own mathematical stories in the language of the East. The mathematical revolution was about to begin.
The hero of this story is a master of disguise. To some people, he's appeared as a wedge shape. To others, as a cone. But no matter what shape he may have taken on, he's always been number one. His story is our story. It's a story of struggle, of knowledge, of where numbers come from. We'll see how one helped create the first cities, how he helped build empires, how he inspired some of the greatest minds in history, and we'll also find out his part in making money work as it does. Oh, thanks. And finally, we'll see how one teamed up with Zero to dominate the world we live in today, the digital world, a world that runs on ones and zeros. These words that I'm now speaking were first written down on my computer using a code of ones and zeros. Even my image coming into this digital TV has been sent through the ether as a series of ones and zeros. So how did these two digits come to dominate our world? They didn't always. In fact, for most of human history, zero simply didn't exist. It's one that really counts. So where did one come from? Well, his story begins at the dawn of time. 3,042,659 years ago to the day, the first primitive one crawled out of the primordial soup onto dry land. Not really, just joking. In fact, the origins of one are shrouded in mystery. It's a mystery that only our earliest ancestors can answer. At some point, one of them must have been the first human being to use one to actually count with. But when? Ever since man could make marks on bones, he's been, well, making marks on bones. But what about the fellow who scratched marks like this 150,000 years ago? Is it possible that he could have been counting? Could these scratches represent a series of ones? Well, the experts tell us that, giving due weight to the scientific and archaeological evidence, they haven't a clue. What they're now pretty sure about is that one is a lot younger than us. It's not until quite recently, a mere 20,000 years ago, that we get the first really solid evidence that one existed and that someone was using it for counting. Of course, he didn't look like this when he was born. Back then, 1 was just a scratch on a bone. This bone. It's known as the Ishango bone.
It was found quite recently in the Congo. And look, you can see these scratches. We know that each represents a 1. How can we be so certain? Well, someone must have been counting, because there are 60 scratches along this edge of the bone and another 60 along this edge. And on the back, they're in equally numbered groups. And you can't do that without counting.
The Ishango bone may mark a defining moment for mankind. Zoologists tell us that other mammals are able to count up to 3 or even 4, but not beyond. By turning 1 into a scratch, our early ancestors could count to 4, 5, 6 if they were all clever clogs. In fact, they could count any number of 1s they wanted. And that is what gave us the edge over the lions and the tigers. From now on, counting knew no limits, and 1 was growing up into a big boy. In the meantime, human beings were moving up the property ladder. And that would change 1's story forever. They stopped living in caves and started to build their own caves, houses. The next great event in 1's life was to happen in the ancient civilization of Sumer. Here in the Middle East in about 4th... there you are. Around this time, the people of Sumer decided to give 1 his independence. They stopped scratching on a bone and set him free by representing him as a token. This transformation changed not only 1's life, but the course of history. The invention of tokens allowed the Sumerians to do something that nobody had done before. If you add notches to a stick or a bone, you can do just that, add. But with tokens, you can take away. So, say you've got 6 chickens and you eat 5 of them. Well, look what you've got.
Indigestion.
No. You've invented arithmetic. It was the biggest breakthrough in 1's life so far. But why did it happen here? To find out, we have to go somewhere where it didn't. Meet the Walpuri of Central Australia. They're people who've been minding their own business here for 30,000 years or so, until some anthropologists came along and noticed that they didn't use numbers.
People get very interested in Walpuri because in our language we don't use numbers. We have a word for 1, but that's about it.
Until recently, the Walpuri have got by without using numbers. How on earth have they been able to manage?
The things that you do in your world are done differently here. Take Jabulari here. He never grew up with any numbers at all. Never Jabulari. I'm not Martada. Kendra. Kalaminata Kurodo.
Pun. Bijan.
Jabulari names his grandchildren. What he doesn't say is 4. It's just not in his vocab.
Pun.
Older generation Walpuri don't talk in terms of exact times of day, just the position of the sun. They don't even deal in distances because their land is mapped out not with numbers, but with songs, which contain all the information they need. These timeless songs, deeply rooted in their culture, are a source of huge national pride.
I should be so lucky, 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 lucky in love. I should be so lucky in love. Oh yeah, I should be so lucky, lucky, lucky.
The fact is, in traditional Walpuri life, they didn't really need a number system, let alone arithmetic. So why, on the other side of the world, 6,000 years ago, did the people of Sumer feel the need to turn one into a token and invent maths?
What was so different about life in the Middle East? I mean, why were people here so keen to get into maths, of all things? Maybe it was because there were so many people living in the same place.
Unlike the Walpuri, the Sumerians lived in cities, and cities need organizing. Grain had to be stored and distributed, and working out how much each person should get required arithmetic. That's why the Sumerians turned one into cone-shaped tokens. Tokens made possible the arithmetic required to assess wealth, calculate profits and loss, and, more important perhaps, collect taxes. Yes, you can blame the invention of maths on city life.
The ability to do arithmetic wasn't the only thing the Sumerians needed for their civic programs. They also needed to be able to keep a permanent record of their calculations. But hold on, the written word hasn't been invented yet. Numbers, it seems, were the world's first writing.
It happened like this. Specific numbers of cones would be put into clay envelopes for safekeeping and then sealed up. But once you'd sealed the envelope, how could you remember how many cones it contained? Bit of a problem, that. But wait a minute. They took another cone and made the same number of impressions on the outside of the envelope as there were cones inside. Then some bright spark realized you didn't need the envelopes in the first place. In fact, you didn't even need the cones. You could just make the marks straight onto a clay tablet, and hey presto, you had a record of the number. The notion of writing had been born. Sumerian mathematicians were now able to keep permanent records of their calculations, and these could become more complex than ever before. Only a select few were initiated into the mysteries of numbers, and they were trained from childhood. They became a powerful and highly paid elite that we still pay homage to today. That's right, the Sumerians' great gift to the world, the chartered accountant. One was now disciplined and organized as never before. He became a powerful tool, one that could be used to build empires, which is precisely what happened to one in his next incarnation. In the hands of the Sumerians, one had become part of a complex counting system. The Egyptians were going to stretch his talents even further. As well as walking very slowly, not smiling and standing in formation, Egyptians loved big things, big buildings, big statues, big armies. They also came up with some really big numbers. And the way they wrote them down provides a fascinating reflection of the hierarchy of Egyptian society. First come the numbers of drudgery and everyday toil. One was a plain, unadorned line. 10 was a rope. 100, a coil of rope. All humble workaday numbers. But then come the numbers for aristocrats, numbers to impress. 1,000 is a lotus, symbol of pleasure. 10,000, a commanding finger. And then the number for pharaohs, a number the Sumerians never even dreamt of. 1,000,000. The sort of number only a pharaoh would need to count his prisoners. It was the first ever million, and the symbol they used was a prisoner begging for forgiveness. Or was it the accountant begging to be let off counting any more prisoners? In any case, one had never been busier. But one had another job the Egyptians wanted it to do, perhaps the most important job of all. They needed him to help out on the building site. The ancient Egyptians were enthusiastic builders with a keen eye for beauty. But you can't create beautiful buildings without measuring things accurately. And you can't measure accurately unless you know what your unit is. That is, what you mean by one. In solving this problem, the Egyptians would do something nobody had done before. They defined their own version of one. They based it on the length of a man's arm from elbow to fingertips, plus the width of his palm. One was now known as the cubit, the measure of everything. The undisputed ruler. These official wands, the master cubit sticks, were so important they were jealously guarded in the temples. From them, copies were made and given out. So right across the empire, whatever the building project, everyone knew what they meant by one.
And with this simple measuring stick, the Egyptians were able to complete their vast construction projects with astonishing accuracy.
If one hadn't become the cubit, some of the wonders of the world might have been, well, a little less wondrous. By transforming one from counting things to measuring things, the ancient Egyptians hadn't just opened up a whole new world of bespoke tailoring and fitted carpets. They had made one the measure of all things. One had become the ruler. But its destiny was even more special. One was about to become the essence of the universe. It all began about 2,500 years ago in ancient Greece, or modern Greece as it then was, because of a chap by the name of Pythagoras. Pythagoras. Did he have a theory or something?
The square of the hypotenuse in a right-angled triangle is equal to the sum of...
That's right, Pythagoras' theorem. Bit of a bore, I never quite understood it.
Well, actually, I think that Pythagoras was a pretty interesting bloke.
Oh, yeah?
He had a school in which all his pupils had to give up their worldly possessions, eat only vegetables, and swear never to touch beans.
Why on earth not?
Pythagoras believed that when you fart, a bit of your soul escaped.
Amazing what you learn in schools nowadays, isn't it? It's true that Pythagoras was a little, well, weird's about the only word for it. He studied in Egypt and the Middle East, and on his return home set up his vegetarian school of maths. Here he devoted himself to exploring the wonders and mysteries contained in numbers. Pythagoras was the first man to come up with the idea of odd and even numbers, and he gave them sexes. 1 was male, 2 was female, and so on. He also had a thing about whole numbers, collections of ones. He realized that certain whole numbers make pleasing shapes. 3 makes a triangle. for a square. 1 plus 2 plus 3 plus 4 makes 10, which forms a magic triangle. Pythagoras was also convinced that 1 would eventually help explain one of the fundamental philosophical questions of the day. The Greek philosophers were forever trying to find out the one thing that everything is made of. One philosopher said everything's made of fire, another air, another water. Pythagoras said that everything was made of numbers, including music. To find out what Pythagoras meant, I've come to the Waterbury Garden Centre in Oxfordshire. Oh, thank you very much. All I need now is a mathematician.
Oh, I'm a mathematician.
Oh, what a bit of luck.
But if you want to find out about Pythagoras' music and maths, we're going to need some pots of rather different sizes.
Good Lord.
Perfect. Pythagoras wanted to understand why certain combinations of notes sounded so beautiful and harmonious. So if we play a pot, we get a note, la. But if I combine it with the note of this pot, la, it's rather a bad combination. Let's listen to them together.
Oh, yes, that doesn't work at all, does it?
But if I play this pot here, la, la, that's a beautiful combination. Let's hear them together. But why is it such a beautiful combination? And the answer is mathematics. The relationship between the weights of these pots is in a perfect 1-to-2 relationship. And it's that combination of whole numbers which makes this such a nice sound. As opposed to the first pot, this is sort of a 1 to 1.264, not a nice whole number relationship, which is causing the bad sound.
So Pythagoras is saying that the harmonies are combinations of whole numbers.
That's right.
Numbers that are collections of ones.
Pythagoras realised that these whole numbers are really why things sound so beautiful, and it excited him so much he realised that really mathematics was the base of everything, that it would explain musical harmony and the cosmos, and this is why he coined the phrase the music of the spheres. So, shall we?
Oh, I don't see why not, yes. If the beauty of music relied on whole numbers, Pythagoras reckoned, so too must everything. And since whole numbers are collections of ones, one must be the essential material out of which the universe is constructed. One had never been so admired. But ultimately, Pythagoras' whole belief system was doomed. And ironically, it was the triangle that made him famous, which was to prove his undoing. If one was at the heart of everything, it should also be at the heart of every triangle, even the right-angled triangle with 2 equal sides. The problem is, it's not. Pythagoras kept trying to make all 3 sides an exact number of units, but it just couldn't be done. When one of his disciples tried to point this out, the others drowned him. Pythagoras' whole belief system that the world was made up of units was a lie. Poor old Pythagoras, brought down by his own favourite geometrical shape. One, however, was about to embark upon a new career. Only first, he would have to become a little less real. Like everyone else before him, Pythagoras couldn't conceive of numbers unless they represented actual things. One was not a one unless it stood for one chair, or one step, or one television presenter. But the mathematicians who followed Pythagoras broke free of these constraints. Yep, Archimedes, famous today as the world's first streaker, but in fact the greatest mathematician of ancient times.
Eureka! Eureka!
Archimedes just loved playing games with numbers, and he took mathematics into the realm of the unimaginable, because in these games he allowed numbers to do impossible things, like working out how many grains of sand you'd need to fill the universe. And yet, daft as some of these mathematical games may seem, they sometimes came up with practical results that we benefit from to this day.
For example, he was obsessed with what would happen if you took a sphere and turned it into a cylinder. What would be the difference in area covered? Well, personally, I don't give a fig. But for Archimedes, it was the proudest moment of his life when he finally succeeded in working out the formula. And although it was a piece of pure mathematical bravado, it did actually prove to be amazingly useful in the end. Because thanks to Archimedes, later mapmakers could take the globe and turn it into a flat map.
One was no longer the essence of the universe, but he was helping to create a golden age of theoretical mathematics. But a new force was at large in the world, and one was about to be dominated by a people who had rather different obsessions. Archimedes lived in Syracuse, and when the Romans invaded in 212 BC, he was in the middle of a particularly gripping piece of calculation. In fact, he was so wrapped up in his work that all he could say was, "I beg you, do not disturb this." Perhaps not a wise move.
It was the end of theoretical mathematics in the classical world. The Romans weren't interested in airy-fairy abstractions like how to calculate the weight of all the goats who ever lived. They were interested in power.
Whether he liked it or not, one was now a servant of Rome. He had to leave the dizzy world of abstract mathematics behind him and get on with more practical concerns. He became the backbone of the Roman world, as the Romans used him to impose a rigid numerical grid on their army. There were 10 men in a section, and 10 sections, 100 men, were called a century. 2 centuries were called a manipulus, which means literally a handful, which I imagine 200 Roman soldiers probably were. Even punishments were dealt out on numerical principles. If a legion suffered a humiliating defeat, the entire legion was decimated, from the Latin word for 10, decem. Regardless of individual guilt, 1 soldier in 10 was killed.
The great aim of the Roman world was to keep things ticking over. Theoretical mathematics just wasn't them. Mark you, I'm not surprised. I mean, the Roman numerals don't exactly make it easy, do they? I mean, look at them.
They're just an elaboration of the old notches on a bone, the only sophistication being new symbols as the numbers get more unwieldy. V for 5, X for 10, C for 100, up to their symbol for 1,000,000. But it's still just a simple counting system, fine for writing inscriptions on tombs, but not much cop for the complications of theoretical maths.
Well, you try writing 1 billion like that. In modern numerals, it takes me about 8 seconds. I tried it. In Roman numerals, it would take something like 16 minutes.
It's no surprise, then, that Roman numerals weren't even used for calculating. The actual calculating had to be done on a counting board, an early version of an abacus. The numerals themselves were just used for recording the results. Maybe it's no coincidence that, unlike the Greeks, not a single Roman mathematician is celebrated today. As Roman power spread, so too did its numeral system. Over the next 500 years, all of Europe, from Spain to Turkey, came under Roman control. And even when their empire eventually crumbled, their numerals were left standing. But though the Roman system might have seemed indestructible, it wasn't. Its nemesis came from the east, to be precise, from India, in 500 AD, or thereabouts. One had an Indian cousin who for some time had been living in a more rarefied atmosphere. The Indians seem to have been less concerned about military organization than about renouncing the world and finding enlightenment. But Nirvana isn't just down the road. To reach it is a very, very long journey, which takes a very, very long time. And to convey that fact, the Indians came up with some stupendously big numbers. Take a raju, for example. A raju is the distance covered by God in 6 months. If he travels 1,000,000 kilometers in every blink of his eyelid. Or how about a pallium? A pallium is the length of time it would take me to build a cube of lamb's wool 10 kilometers high, if I were to lay 1 strand every century. Here's one I made earlier. Well, these were the sort of numbers that could have made one feel, well, small, if he hadn't had a little help from his friends. Unlike the Romans, the Indians devised a system that could cope with vast numbers. They developed a different symbol for every number from 1 to 9. 1, 2, 3. Or if you do them quickly, you get Arabic numerals.
नहीं है, अरबी नहीं है, ये हमारा हिंदुस्तानियों का बनाया हुआ है. हम लोग हिंदुस्तानी इसे 2000 वर्ष पहले से प्रयोग कर रहे हैं.
He's right, you know. The numbers we use today are called Arabic, but in fact, they began life here in India as early as 500 BC. But then, around 1500 years ago, or a little longer if you're watching a repeat of this program, someone came up with a stupendous, incredible, extraordinary idea. The biggest revolution in numbers since the Sumerians invented maths. A creation that would change the world. They invented an entirely new number. And it's in here, inside this tiny 1100-year-old temple in Gwalior, northern India, is this new number. And after a 4,000-mile journey, I'm finally going to get to see it. Nick, it's locked. So we wait. And while we wait, I start to wonder, how was it that this new number wasn't invented sooner? It's such a simple little number that takes only a moment to say and even less to write. Ah, here he is. But once invented, it transformed the life of one in a way that would eventually change the entire world. Well, here we are. The first undisputed example of India's greatest invention. The new number. The holy grail of numbers. 0. For the first time in human history, someone had made nothing a number. The inscription says that a garden was planted to produce flowers for the temple. And to ensure that they had enough, that garden had to be 187 by 270 hastas, about 20 acres.
Well, while the Romans were using numbers to record their conquests and count dead bodies, these people were using them to make sure they had adequate supplies for their flower arrangements.
Well, you might say, what's all the fuss about? I mean, what's so wonderful about inventing a symbol that means nothing? I mean, if somebody asks me how much I've got in my hand, I can just say, well, I haven't got anything in my hand. I don't need a zero to do that. Well, a zero on its own would be nothing, well, obviously. But when you teamed zero up with one, magic started to happen. And when they were joined by the rest of the troop, the results were spectacular. With just 10 digits, the Indians could make numbers infinitely large, as well as infinitely small. Now, the Romans couldn't do that. One had found his perfect mate in zero, and it was a partnership that was going to change the world. Together with the rest of the team, they enabled Indian science to storm ahead. Indian astronomers, for example, were centuries ahead of the Christian worlds. Indian scientists worked out that the Earth spins on its axis and that it moves round the sun, something that over in Europe, Copernicus wouldn't figure out until 1,000 years later. Indian scientists also calculated the diameter of the globe, and they were less than 1% off what it actually is. All this was possible because of 1, 0, and the rest of the troop of performing numbers. They were a sensation, and their fame soon began to spread across the globe. A conflict with the numbers of Rome was bound to happen sooner or later. But for now, 1 and 0 and their friends made their way across the deserts of Arabia to take on one of the most sophisticated societies of the age, in what is now Iraq. When Islam was little more than 100 years old, Baghdad was ruled by the great Caliph Al-Mansur. Now, the Caliph wished his people to live according to the Quran, so he set up courts and judges to apply the law of the Prophet. Now, the law of the Prophet is full of instructions that require serious mathematical calculations if they are to be carried out exactly. For example, unlike Christianity, the Quran insists that women share in any inheritance. The book says there is a share for men and a share for women, each share depending on the number of other relatives and their relation to the deceased. Working all that out required fractions and ratios, but these were people who counted on their fingers. It's not like they weren't up to complex arithmetic, it was just their number system was holding them back. But one day, there arrived in the court an ambassador from India. He had to present the great Caliph with a gift of some sort. But the Caliph was a man of infinite riches. It was hard to know what to give. I mean, an I Love India t-shirt was hardly going to do the job. The ambassador, however, had thought long and hard about this, and had decided to present the Caliph with the greatest gift he could think of. The gift of numbers. Actually, we don't know for certain exactly how Indian numerals came to be adopted in the Islamic world, but the ambassador story is my favourite. what we do know is that Muslim scholars were bowled over by 1-0 and the rest of the troop. And the most famous of these scholars was a man by the name of Al-Khwarizmi.
Al-Khwarizmi.
Al-Khwarizmi. Khwarizmi?
Al-Khwarizmi.
Al-Khwarizmi.
That's right.
Al-Khwarizmi and his colleagues taught the performing numerals a whole host of brand new tricks. Quadratic equations, algebra, reversed, logarithmic, cubic cake, handstands. Well, okay, I made that last one up. But these new numerical feats enabled science, mathematics, and astronomy to reach new heights in the Middle East. And the Indian troop became a smash hit throughout the Islamic world. But on the other side of the Mediterranean, Christian Europe was still in the static grip of the old army of Roman numerals. And being Romans, they weren't going to give way to the feisty newcomers that easily. A showdown between the two systems was inevitable, and when it came, it would shape the destiny of the Western world. The beginning of the end for the Roman numerals started on the shores of North Africa. Muslim traders had been quick to adopt 1-0 and co. for their business dealings. By the end of the 12th century, the Indian numerals were in common use. And it was in the bustling port of Béjaïa that the young son of an Italian diplomat based in Algeria first witnessed their amazing act.
When I had been introduced to the art of the Indians' 9 symbols, knowledge of the art very soon pleased me more than anything else, and I came to understand it.
That young man was known as Fibonacci, and he was so knocked out by the Indian numerals that when he grew up, he decided to take them home with him. In 1202, Fibonacci wrote a book all about calculation called, well, the Book of Calculation. He's now regarded as one of the greatest mathematicians of all time, and his book was pretty much a showcase for Indian numbers.
Fibonacci wasn't just an ivory tower theorist. Part of his Book of Calculations was aimed specifically at merchants, showing them how useful Indian numerals could be for, say, calculating their profits.
Not exactly a page-turner, you might think, but this was a time when capitalism was beginning to come out into the open in Europe. Fibonacci's book was a must-read. Unfortunately, ordinary people felt comfortable with the old numbers. After all, they'd lived with them for the best part of 1,000 years. The old Roman numerals weren't going to make it easy for the Indian newcomers. And it wasn't just a question of tradition. Your average punter had some pretty good reasons to prefer the old system.
For example, many medieval Italian cities had their own currency. So every time I found myself at a new town or a new set with extras in costumes, as the case may be, I have to go to the money changer's bench, or banker, as it's called.
A banker was a counting table, basically an abacus with counters instead of beads. The men who operated them, the bankers, had to swear an oath not to cheat their customers.
Mind you, if the magistrates find he is cheating me, they'll come and break his bench, and his banker will be rupta, which is the word for broken. And he'll be declared bankerupta, which is where we get the word bankrupt from. Hi.
Now, these things, how much can I get for those in whatever place this is? Well, he's
counting it now. It's reassuring to see he's using numerals I'm familiar with, which are Roman numerals, of course. And he's using this abacus, so at least I can see what he's doing. And I get that much. Oh, right, fine. Well, thanks a lot. Nice doing business with you. But what if I was to go over to one of the smart chaps using the newfangled Indian numerals? Hi. Now, how much would you give me for that? Now, you see, this is the problem. You see, as a medieval punter, I've got no idea what he's writing. I mean, no wonder people were suspicious. I mean, if my bank started keeping my accounts in Chinese, I'd be suspicious. Oh, thanks. I've got no idea how you arrived at that. But thanks anyway.
This distrust went right to the top. In 1299, the city of Florence actually banned merchants from using the new numbers in accounts. They had to use Roman numerals. But no number was treated with more suspicion than one's partner, zero. One writer called zero a sign which creates confusion and difficulties.
Zero was called cipher, and it was regarded with such suspicion that that word became our word for secret code, a cipher.
But the days of the old system were numbered. And I suppose you could blame good old human greed. The traditionalists who clung to the abacus and Roman numerals had never had to calculate interests on loans because the Catholic Church said charging interests on loans was a sin. It was called usury. But come the Reformation, the Protestant churches were more business-friendly, and the long-held Christian objections to capitalism seemed to, well, disappear. So, in this new money-lending, interest-charging environment, which would prove the more useful, Indian numbers or the abacus? Well, let's find out.
On my right, one first-class mathematician. On my left, one first-class abacist. So, supposing I lend someone £10 at 0.5% interest a month, how much do they owe me at the end of the year? Okay? Ready? Steady? Go!
Kimmy's been an abacist since she was just 15 and is using a modern Soroban model. But just as they did in the 16th century, she's rounding her numbers to the nearest penny as she goes. Let's hope she can round herself up into first place. Marcus is using a pen and paper, so he's working to an eye-popping 12 decimal places. He lives in North London with his lovely wife Shani and 3 charming children. He's not big, but he is clever.
The Kimmy has got an answer. Kimmy,
yes.
What's your answer?
£10.60.
£10.60. Yes. So compound interest after a year would be £10.60, and the abacus seems to have got there before the mathematician.
Well, I don't want to put a damper on things, but I think that answer is actually wrong. I've got an answer of £10.61.6777664035 to be precise. I've actually picked up the subtlety of compound interest, which is it's a little bit each month, but it adds up, so I've got this extra 1.67p.
For the medieval businessman, it would mean the difference between making a living and not. Maybe that's why the abacus user looks so miserable.
As capitalism gained respectability, calculating interest and compound interest became de rigueur for any self-respecting businessman. And for doing that, even with an abacus, the old Roman system was simply no match for the Indian numerals.
So, centuries after Fibonacci had brought them to Europe, the Indian numbers finally outmaneuvered the lumbering old Romans. They were quick and versatile, and with 1 and 0 in the lead, just better at teamwork. When the end came, it was a pushover. The old Roman numerals were at last bancarupta. But 1 and 0 had even bigger plans for the future. And they didn't include the other numerals. In the meantime, the full troop of Indian numbers took over the Western world. With them, European navigators found it easier to calculate their latitude, and so dared to cross the great ocean out of sight of land. That's how they stumbled on America. And the new numbers became the vocabulary of modern banking as we know it.
Hello.
But there was still plenty of room for that old problem, human error. Columbus thought he'd got to Japan, when in fact he'd got to the West Indies, half the world away. He'd made a mistake. Humans do, which was something one man was determined to stop. It all happened around about 16... Oh, there you are, you've got it again. Gottfried Wilhelm Leibniz was one of the greatest mathematicians of all time. He set out to rid mankind of the curse of human error. In trying to do this, Leibniz invented something that still affects us every day of our lives. What's more, it's an invention that was to give our old friend Juan the chance to rule the world. Leibniz was convinced that he could eradicate error by inventing a mechanical calculating machine. And in fact, he built one, using all the numerals from 0 to 9. But then he had a better idea, and it was one that was inspired by his philosophy.
It is true that as the empty voids and dismal wilderness belong to 0, so the Spirit of God and his light belong to the all-powerful One.
In other words, to paraphrase Leibniz very, very, very loosely, the universe is a bit like a Swiss cheese, which some of us have suspected for years. The holes are just as important as the cheese itself. So to construct the world, you need both something, good old number 1, and also lots of nothing, which is where 0 comes in. Leibniz was convinced that 1 and 0 were the only numbers that anyone really needed. With these two numbers, he claimed, he could achieve every mathematical dream, and, what's more, eliminate human error. So he got rid of the other numbers and developed a system using just 1s and 0s. It's called the binary system. And yet, wait a minute, how could you possibly express all numbers just with a 1 and a 0? I think it's time I spoke to someone who knows what he's talking about. Marcus! I need to understand the binary system.
Binary. Okay, let me give you a number in binary.
Okay.
Here is the number 9 written in binary.
So this is just using 1s and 0s
1s
to
and
express
0s.
any number.
It's just 0s and 1s. So that's 9 in binary.
Well, it looks like 1001 to me.
That's because you're obsessed with your 10 fingers and you like to keep track of things in tens. Well, this one keeps track of how many 1s, the second column of how many 10s there are, next how many 100s, and one lot of 1000s. But in binary, things work rather differently. In binary, what the columns keep track of is how many 1s, how many 2s, how many 4s, and how many 8s there are. Here we have an egg. We're only allowed to represent these numbers using 0s and 1s. Yeah. Okay, so we're only allowed either to put an egg in or not have an egg.
An egg in is 1.
An egg represents 1. So let me show you what 9 is in binary. One lot of 8, so I have an egg in the 4th column.
It's a 1.
Yeah, that's one lot of 8 in the 4th column. And 9 is 8 plus 1, so I need a 1 in the 1s column. So in binary, the number 9 is one lot of 8, no 4s, no 2s, and 1 1.
Amazing. But what about the other numbers? Well, after just 3 short hours of tuition, I began to see that it was possible, after all, to make every number using just 1s and not 1s. What's more, I became convinced that you don't need to do it with eggs. It's a sort of mechanical system.
It's very mechanical to add the ones and zeros, and that's why it's perfect for a machine. And a machine doesn't really care too much about how big the numbers get. It can keep track of very long numbers, whilst we're not very good at doing that. What it's interested in is a very efficient way of adding numbers. That's why machines love to put numbers into binary.
And Leibniz designed exactly such a binary machine. Only his was using metal balls dropping into slots instead of eggs and egg cups. From now on, mistakes would be a thing of the past. The digital age, it seemed, was ready to take over the world. Unfortunately, he never built it. One and zero would have to wait another 265 years before they could step into the limelight. Meet Colossus, the world's first working binary computer. It's Leibniz's dream made real. But instead of dropping metal balls into slots, Colossus is electronic. In here, 1 and 0, something and nothing, have finally come into their element as electrical currents, on and off. Colossus was created during the Second World War and installed here in Britain's code-breaking centre at Bletchley Park. It has 1,200 valves, miles of wires, hundreds of mechanical components. But just like all computers today, the beating heart of this machine is 1 and 0. In their electronic binary form, 1 and 0 performed millions of rapid calculations, enough to crack the enemy's codes before the Germans had even sharpened their pencils. Thanks to Colossus, the Allies knew what the German messages said even before Hitler did. And it may be that this extraordinary contraption helped shorten the war by as much as 2 years. The technology that started here in Bletchley has changed our world forever. You remember all those reasons for using and understanding numbers, doing astronomical calculations, working out measurements, and juggling with the divisions of property? Computers can do it. Working out percentages, currency exchange rates, and compound interest. All that calculation that preoccupied and sometimes perplexed the great minds of antiquity. Just leave it to the computers, and we can all simply be happy ignoramuses, not even knowing whether the answer's right or wrong. And that's got to be a good thing, isn't it?
Terry? Where are you going, Terry? I say, you're not leaving me, are you, Terry? Terry! Terry!
In the computer age, our whole world runs on a stream of ones and not ones. From our bank statements and medical records to the barcode every time I buy a tin of cat food. And the rest of the numbers can be consigned to the dustbin of history. 1 and 0 are all we need. The old performing duo have come out on top. Let's just hope we can control the little blighters.
Well, I thought I was rather good, didn't you?
I thought you were marvellous.
Sublime.
I would
They
they?
kept my
And the
astronomy.
I much preferred working with Michael Palin.